This video is sponsored by Incone. More on them later. It's just another quiet morning in the city of Batam, Indonesia. Yet, as large metal pieces begin falling from the sky, crushing rooftops, its residents quickly learned that something is amiss. Only a few thousand feet above, the world's largest passenger aircraft carrying over 400 passengers is experiencing a dire emergency. One of the engines has exploded and the damage has crippled critical systems, leaving the remaining engines struggling to keep the giant aircraft in the air. The crew needs to return and land. But as more warning messages pop up indicating a potential fuel leak and flight control issues, the stakes are higher than ever. Return right away and they risk losing control of the aircraft before landing. Stay up in the air to test the aircraft systems and ensure full functionality, and they may lose too much fuel to safely make it back. A tiny defect caused a chain reaction. Now over 400 lives depend on what happens next. This is the story of Qantas Flight 32. It's the morning of November 4, 2010. A Qantas Airbus A380 operating as Flight 32 is taxiing for departure at Singapore's Changi International Airport. Singapore is a scheduled routine stopover for this flagship Qantas route originating in London. The aircraft is carrying a total of 440 passengers with 24 cabin crew members and a 5-pilot crew in the flight deck, with Captain Richard Champion de Crespigny at the helm. Captain de Crespigny is a former military pilot with a total of over 15,000 hours of flight time. He is joined by First Officer Matt Hicks with 11,000 hours of flight time and Second Officer Mark Johnson, who has accumulated a total of 8,000 hours of flight time. The role of a second officer on this flight is to act as a relief pilot during cruise, allowing one of the other 2 pilots to leave the flight deck and take a rest. Although these flights are typically operated by just 3 pilots, today Captain de Crespigny is being monitored and evaluated as part of an annual route check, a standard procedure at Qantas. His check captain, Harry Wubbin, with a total of 20,000 hours of flight time, is undergoing training for this role. Therefore, he is also being monitored by a supervising check captain, David Evans, who has accumulated over 17,000 hours. With a combined total of more than 70,000 flight hours and years of experience, it is safe to say that this veteran flight crew is very skilled and knowledgeable. They are well suited to take on the many challenges associated with operating the largest passenger airliner in the world, for an airline that has not had a fatal accident since the 1950s. But are they prepared to handle what is going to happen next and to keep an impeccable safety record? At 9:56 a.m. local time, Flight 32 lifts off from Changi's runway 20 center. Loaded up with enough fuel for the 7.5-hour journey back to Australia and 469 people on board, the aircraft begins its steady climb to cruise altitude. Nothing in the cockpit is an indication that things are about to turn for the worst. But only 5 minutes after takeoff, as the airplane is climbing through 7,000 feet, the flight crew hears 2 loud bangs coming from the left side. Right after the Airbus yaws to the left, suggesting that one of the engines has likely failed, a warning message appears on the Electronic Centralized Aircraft Monitoring (ECAM) system, indicating that the turbine inside engine number 2 has overheated. The captain decides to level off the aircraft and assess the situation. As he programs the autopilot to maintain 7,400 feet and 250 knots of airspeed, he notices that the auto throttle system is not working. Just another sign of trouble and an additional hurdle to worry about. Once confident that the aircraft is controllable and stable, the captain asks the first officer to start addressing the ECAM warnings. The ECAM checklist for an overheating turbine directs the pilot to move the thrust lever for engine number 2 to idle and monitor it for 30 seconds. The crew follows the instruction and decides to transmit a pan-pan message to air traffic control and inform them of the situation while they wait for 30 seconds. Different from a mayday call that signals an emergency and the need to land immediately, a pan-pan call is used to inform air traffic control that an urgency exists. And although assistance may be required, the situation is not dire at the moment. The captain ends the call with a "stand by for instructions" message, a request to not disturb the flight crew so that they can focus on dealing with the aircraft first. It's a great example of the classic aviate, navigate, communicate mantra taught to every pilot early on in their training. Moments later, another ECAM message appears indicating a fire in engine number 2. Within 3 seconds, the alert goes away. Considering the overheated turbine message and fearing that a fire may be developing, the pilots decide to shut down the engine and discharge fire extinguisher bottles installed inside the engine. As they try discharging the first bottle twice, they get no result. Confused, they try discharging the second fire extinguisher bottle. After multiple attempts, the crew has no confirmation that either of the fire extinguisher bottles has been discharged. After a quick discussion, they decide to continue following the procedure for an in-flight engine shutdown and begin transferring the fuel from engine number 2. A quick look at the engine indicators shows that engine number 2 has failed. Engines 1 and 4 are running in a degraded mode, and engine number 3 is running in an alternate mode. The alternate and the degraded modes indicate that the onboard computers have stopped receiving one or multiple parameters from the engine. Although the engines are still producing power, they have to be managed by the pilots manually as the onboard automatic systems cannot control the engines anymore. In the cabin, the passengers and the flight attendants seated on the left side of the aircraft can see that the wing has been damaged and fuel is pouring out of the fuel tank. One passenger notices a small fire inside the wing. Anxiety and fear begin to spread around the cabin as everyone prepares for the worst outcome. To get an update and share their observations, the customer service manager and other flight attendants are trying to call the flight crew using the emergency intercom function. Despite their attempts, cabin crew members get no response from the flight deck. The pilots are completely overwhelmed by a continuous inflow of ECAM messages concerning other aircraft systems and do not notice the call from the cabin. One after another, ECAM alerts pop up showing that the flight controls, fuel, electrical, braking, and hydraulic systems have also been affected in one way or another. Overall, out of 22 total systems on the aircraft, 21 are malfunctioning. A pilot's worst nightmare come true. It is becoming obvious to the captain that the situation has grown beyond the simple engine failure scenario practiced in airline pilot training. A more serious situation is at hand. Still not sure what exactly has happened, the crew must choose whether to land immediately or address the many critical failures first. It is the first of several important decisions that will have to be made during this flight. Attempting a landing in the battered aircraft may prove to be disastrous if the flight controls are severely affected, while staying up in the air with an active fuel leak creates a risk of an engine-out landing. It is a tough spot to be in as a captain. After spending some time on an internal discussion, the crew makes a determination that they have full control of the aircraft and sufficient fuel to remain airborne while they work through dozens of ECAM messages and run the appropriate checklists. The captain makes a public announcement using the aircraft's intercom system to give the passengers an update on the situation and to let them know of their intentions to troubleshoot the failures. The first officer advises air traffic control of their decision and requests directions for holding near the airport. ATC instructs Flight 32 to fly a 20 nautical mile-long racetrack holding pattern just east of Changi Airport. Furthermore, they inform the crew that aircraft parts and pieces have been found on the ground. Several fragments of the turbine disc flew over Batam, Indonesia, landing on residential buildings and city streets. It was only by pure luck that nobody on the ground got hurt. As the news about aircraft pieces falling from the sky quickly spreads around the world, there is still no confirmation from official sources. With so little information available, it is rumored that a Qantas super jumbo jet has crashed over Indonesia. Before we discuss further actions of the crew and the outcome of the accident, it is a good time to cover what caused engine number 2 to fail as well as the extent of the failure, something that the crew can only guess but has no full understanding of at this point. Due to a misalignment within the machinery at the engine manufacturing plant, an oil feed stub pipe, a pipe designed to transfer oil inside the engine, was drilled unevenly, making it much thinner on one side. Over time, a fatigue crack started to develop on the thinner side of the pipe until it grew big enough to let out a significant amount of oil inside the hot engine. Due to the high operating temperature within the engine, the oil spraying out of the oil feed pipe quickly ignited and caused an internal explosion which was strong enough to break apart one of the turbine discs. Rotating at an extremely high speed, the fragments of the disc broke through the engine casing, puncturing the wing and the fuel tank near engine number 2 and cutting through the wiring laid out inside the wing. One of the hot fragments broke through the wing fuel tank and ignited the fuel vapors, causing a small fire inside the tank. The damage to the wiring caused the loss of monitoring of the fluid level, system pressure, and reservoir air pressure of the green hydraulic system, forcing the crew to shut it down following the ECAM checklists. As a result, some aircraft controls were no longer operational. These included all wing slats, outboard ailerons on both sides, some landing gear brakes, and approximately one-half of wing spoilers. Although the crew also had to shut down half of the pumps powering the second hydraulic system, it remained fully operational, and aircraft flaps, elevators, and rudders were still working properly. Having entered the holding pattern east of Singapore, the flight crew begins the process of troubleshooting the failures and evaluating the condition of the aircraft. For the next hour, the pilots go through over 100 checklists that had been queued in the ECAM since the failure, addressing one fault after another. In the meantime, the second officer leaves the flight deck to visually assess the damage to the wing. One of the passengers, a fellow Qantas pilot, shows the second officer a live feed from the tail-mounted camera available to all passengers via the in-flight entertainment system. The camera shows a large streak of fuel exiting the left wing, confirming the crew's suspicion of a fuel leak. As he approaches the middle section of the cabin to look outside, the second officer notices several holes in the left wing. Passengers seated nearby become even more concerned as they see the pilot's surprised and worried expression. Astonished, he returns to the flight deck to describe the extent of the damage to the rest of the flight crew. Needless to say, the aircraft is in a less than ideal shape, and the success of the recovery will depend on the crew's cooperation. Hence, it is crucial for the captain that all members of his crew share an accurate mental model. In other words, a clear understanding of their situation and the environment. To accomplish the unattainable, he decides to invert the logic, an idea he learned from NASA's Apollo 13 mission. Instead of trying to understand what doesn't work, the crew will focus on identifying what works. Through their review of the aircraft system displays, the flight crew learned that 8 out of 11 fuel tanks of the aircraft were unusable. Furthermore, at least half of the fuel pumps became inoperable, including the fuel jettison pumps, which could allow the aircraft to release some of the fuel, reducing the aircraft's total weight and bringing it below the maximum landing weight. Although most of the fuel is now unusable, the crew determines that they have at least 2.5 hours of fuel available in the tanks to which they still have access. With the fuel problem out of the way, the next item on the agenda is the controllability of the aircraft. Although the crew is able to maintain level flight at this moment, the wing has been damaged and the condition of the control surfaces is questionable. By having to shut down the green hydraulic system and thus rendering some of the control surfaces on the wing inoperable, the crew is now facing a 65% reduction in roll control, or the ability to bank from side to side. Control malfunctions are a possibility for which military pilots train in case their aircraft gets hit by a missile or experiences a mid-air collision. Relying on his Air Force background, Captain de Crespigny decides to conduct a control check of the aircraft. Before a landing attempt can be made, it is crucial for him to understand how the aircraft will handle at lower speeds and with the landing gear and flaps extended. If there are difficulties and complications, it is much better to learn about them at an altitude where there is room for recovery rather than on final approach. Moving the side stick side to side in different flap configurations, the captain monitors the deflection of the control surfaces using the onboard monitors to ensure they respond properly. Satisfied with the results, the crew can finally start preparing for an attempt to land the damaged airliner. To prepare for the landing, the flight crew must calculate the speed at which the aircraft will fly the approach and determine the minimum runway distance required. The calculations are performed using the onboard computer system. After some initial difficulties, the senior check captain is finally able to calculate the landing performance and the required landing distance. His projections show that in its current condition, the heavy aircraft will require nearly the entire 4,000 m of runway 20 center with only 130 m or 400 foot left to spare. Understanding that the landing will have to be very precise with little room for error, the flight crew informs ATC that they are ready to land and requests a long approach. Per the request of the flight crew, by giving out specific heading instructions, ATC vectors the aircraft to fly further north before turning the flight around and setting it up for a 20-mile-long final approach for runway 20 center. While a typical final approach begins around 10 miles from the runway, having the extra 10 miles of distance gives the crew additional time to configure the aircraft for the approach. The extra time is especially important in this case as the aircraft will be in an abnormal landing configuration. A fuel leak in the left wing has led to a fuel imbalance between the wing tanks, meaning that the aircraft is heavier on one side. Due to the damage to the hydraulic system, the leading edge slats cannot be extended, and the wing flaps will only be extended to flaps 3 and not the full setting. As the aircraft turns onto the final approach course, the crew uses the alternative landing gear extension method to release the landing gear from the up position and extend it by means of gravity. The aircraft is now ready for landing, and the flight crew gives the flight attendants a command to prepare for the arrival. Still having control of 3 engines, the captain sets symmetrical thrust for the outboard engines number 1 and 4, while only using engine number 3 for speed control. Only the inboard engines on the A380 have thrust reversers. Hence, engine 3 is also the only engine on this aircraft with a working reverse thrust that can be used to help in slowing down after landing. At 800 feet, the autopilot is disconnected and the captain continues to hand fly the approach as the aircraft descends toward the runway at 1,400 feet per minute, close to double the maximum vertical speed for which the landing gear is certified. The captain is presented with yet another difficult decision. If he gradually reduces the rate of descent before touching down on the runway, the aircraft may float above the runway for too long, thus limiting the length of the runway available for the rollout after touchdown. Touching down too firmly, on the other hand, creates the risk of breaking the landing gear, puncturing the wings, and sliding down the runway while generating sparks near the leaking fuel, a recipe for disaster. Adding to the series of unconventional practices that Captain de Crespigny had to utilize while handling this accident, he decides to quickly push the control stick all the way forward just before the wheels touch the ground. Although it may seem contrary to what a pilot should be doing in the flare, this action rotates the aircraft around its center of gravity, lifts the main landing gear, and creates an additional cushion of air that slows the aircraft's rate of descent and holds it up in the air for an additional second, minimizing the impact on the landing gear. Finally, at 11:46, Qantas Flight 32 touches down on Singapore's runway 20 center, the runway from which it took off a mere 2 hours ago. Deploying only half of the speed brakes installed and with only one working thrust reverser, the captain applies maximum braking in the hopes that he can slow the overweight giant before the runway ends. Anticipating an emergency landing, the airport management has blocked the perimeter road outside the airport to avoid any casualties on the ground in case of a runway overrun. Although this action is helpful in minimizing injuries and potential deaths, the biggest concern is the fate of 469 people inside the A380 that continues to roll down the runway with the other end coming in very fast. Despite the reduction in braking and engine reverse capabilities, the Super Jumbo comes to a complete stop roughly 150 m or just under 500 feet from the end of runway 20 center. It is a testament to the precision and the skill with which the captain handled the aircraft. Once the aircraft came to rest, all passengers breathed out a sigh of relief and gave a loud round of applause. In the flight deck, however, the situation is still tense as the flight crew shuts down the remaining 3 engines. They notice on the onboard information display that the temperature of the left landing gear brakes is over 900 degrees Celsius and rising. With the fuel still actively pouring out of the left wing tank, there is a growing risk of a fire and an explosion. To prevent disaster, the flight crew contacts emergency services already on standby and requests firefighting foam to cover the fuel leak and landing gear. The fire brigade responds with a request to shut down engine number 1. In confusion, the crew verifies that all engine switches have been turned to the off position. Yet, once the captain looks out the window to his left, he notices that engine 1 is still running. Attempting other emergency shutdown procedures has no impact and the engine continues operating. It appears as though the engine and its wiring have been entirely disconnected from the rest of the aircraft. Knowing that the fire crew has covered the fuel leak with foam and poured water over the brakes to cool them down, the captain assesses that the risk of explosion is reduced and there is no need for evacuation. Shortly thereafter, passengers begin disembarking using the airs provided by the airport. While the passengers vacate the aircraft, the flight crew continues making attempts to shut down the last working engine, including pulling circuit breakers to cut off electrical supply to various aircraft systems and reconfiguring the fuel system in an attempt to stop the supply of fuel to the engine. Nothing proves to be a success, and the ultimate decision is made to drown the engine in foam and water by continuously spraying it into the engine. More than 3 hours after landing, at 2:53 p.m., the last running engine on Flight 32 is finally shut down. Crisis averted. Following the events of Flight 32, Qantas grounded the entire A380 fleet for close to 3 weeks until the cause of the uncontained engine failure was identified. Fearing that other aircraft may have been affected, Rolls-Royce, the engine manufacturer, instructed all operators to inspect engine turbines for evidence of oil leaks before the next flight was completed. Furthermore, a long-term solution proposed by Rolls-Royce included a software update with the addition of an intermediate pressure turbine overspeed protection system designed to monitor the speed of the turbine disk and shut down the engine before the critical speed is reached. The story of Qantas Flight 32 is a demonstration of how even small errors in the design and manufacturing process can snowball into devastating results. Captain de Crespigny's quick decision-making and extensive knowledge base were instrumental in addressing the issues as they came. In one of the post-accident interviews, he rightfully stated that we must commit to a lifetime of learning, a solid piece of advice that is applicable within and beyond the aviation industry. Thanks to Incone for sponsoring the video. Don't forget to click the link in the description to get an amazing discount.